Skylab, 100-ton lab complex circling the Earth every 93 minutes for 8 months, the nation's first research laboratory in space. The primary objective of Skylab is to conduct scientific investigations in the areas of biomedical science, solar physics, Earth resources, crew operations, astrophysics, and space technology. Of the approximately 90 experiments performed on Skylab, this film describes 6 experiments, 5 of which involve space photography. The 6th collects impressions of flying micrometeorites so small that they cannot be seen by the naked eye. The 5 ultraviolet and visual photography experiments capture images of hot young stars, the sun, both flaring and in periods of minimal activity, the invisible ozone layer around the Earth, twilight air glow, Earth terrain, and light-carrying particles in space near the sun, in space near Earth, and near the spacecraft itself. This series of experiments utilizes 2 scientific airlocks, which enable crewmen to operate instruments in outer space while working in a shirt-sleeve environment within the spacecraft. All these experiments will help us gain new knowledge about space and also about Earth, knowledge that may shape our future environment. The UV stellar astronomy experiment is designed to gather more information on relatively young stars, some of which are 10 times heavier and 4 times hotter than the sun. These hotter stars appear to the naked eye in a bluish color. Most of these stars are located in the Milky Way and in nearby galaxies. These stars are photographed by a spectrograph, which includes a camera, telescope, and a mirror system. The spectrograph utilizes a prism that filters out everything but the ultraviolet rays emanating from these stars. The crewman installs the mirror system into the airlock. He unstows the optical canister and prepares for installation on the mirror system. The film canister, which records the image, is mounted to the optical canister. It is this unit, the optical canister, that shapes the ultraviolet spectral image of the star. To get the mirror system into space, the crewman rotates the extension knob, which moves the mirror beyond the wall of the Skylab. Because the photos are taken only on the dark side of the Earth, the crewman has about 32 minutes per each selected orbit for picture taking. The crewman rotates the mirror to point to the area of the sky that'll be photographed. The mirror can be rotated 360 degrees and tilted 15 degrees so as to capture the star image in the mirror without maneuvering the spacecraft. The mirror image is then photographed. He introduces motion into the image in order to produce a band image rather than a thin line of light, which gives no details. On each dark side pass that this experiment is conducted, the crewman will try to photograph 3 or 4 star fields, making several exposures on each star for a total of about 12 exposures for each 32-minute dark side pass. After the photographs have been taken, the mirror is retracted into the scientific airlock. This experiment then, after gathering new data from a spectrum of ultraviolet rays being produced by these stars, will deepen our knowledge of the universe. The data gathered will help scientists know the photographed stars better, their origin, composition, temperatures, pressures, and lifespans. The UV solar photography experiment is one of many related Skylab studies of the sun. Solar photographs containing both ultraviolet and X-ray data will be taken by a spectrograph mounted in the airlock during solar flare periods and also during periods of minimal solar activity. Flare data is significant because any increase in ultraviolet and X-ray radiation can disrupt radio communication. This experiment will contribute to knowledge needed for the eventual prediction of solar flares, as well as increasing our overall knowledge of the sun. Each film container carries 2 film magazines and 2 filters, with each magazine containing 10 film exposures. The scientific airlock door is opened, and the bore sighter, a small viewing port, allows the operator to view the sun to make the necessary alignment. After checking for alignment corrections, the crewman gives a voice instruction to another crewman who commands a change in attitude to realign the Skylab. The crewman starts the timed exposure, advances the film, and repeats the sequence for a series of timed exposures. Then the crewman records pertinent data regarding the exposures. While other Skylab experiments are devoted to solar studies, this experiment complements them by providing ultraviolet and X-ray data not obtained in the other studies. The particle collection experiment will study the origin and history of micrometeorites in the solar system. This support unit will house 4 cassettes, each containing 16 detection surfaces consisting of film laminates and highly polished metal. These surfaces, when exposed to the space environment, are sufficiently sensitive to record the impact of micrometeorites. An analysis of the impact marks made on the surfaces will help scientists determine the composition, velocity, and structure of micrometeorites encountered by the detection system in near space. Here the crewman unlocks and mounts the micrometeorite collection device to an extension system that will extend the unit to 18 feet away from the spacecraft. There, the unit will be in a fixed position so that the direction of the particles can be determined. This universal extension system is also used in other experiments aboard Skylab. For instance, a photometer automatically scans the skies and measures light intensity and color, and a TV camera will permit people on the ground to view astronauts on trips outside the spacecraft. Near-space particles have been studied before by means of detection systems such as microphones, pressure cells, and thin-film capacitors. However, this experiment is one of the more comprehensive yet attempted. The experiment is installed into the scientific airlock, and instrumentation and power cables are connected to the system. Then to the workshop power source and data recording system. And the airlock is depressurized and the SAL door opened. The crewman then attaches an extension rod which will push the detection device into space. 2 extension rods are used when the device is being used on the shaded side of Skylab, while 7 rods are necessary on the sun side in order to extend the device beyond spacecraft obstructions and the radiating heat of the spacecraft itself. Temperature on the shaded side of the spacecraft is minus 100 degrees Fahrenheit, while on the sun side, temperatures exceed 200 degrees Fahrenheit. Once the detection device is extended beyond the spacecraft, the crewman actuates the switches that open the detection unit surfaces so that each of the 64 detection surfaces is exposed to particles approaching from many directions. Opening and closing of cassettes may be accomplished by crew or ground control. Another instrument that has been activated by the crewman records the position of the cassette arms and the temperature of the detector package. The detection surfaces, opened up 90 degrees, will be exposed to space particles for a minimum of 72 hours. The cassettes are then removed and returned to Earth. The particle collection experiment makes new advances in the study of the origin and characteristics of micrometeorites in near-Earth space. Another result will be improved spacecraft design. In the UV airglow horizon photography experiment, the crewman uses basically the same equipment to conduct 2 experiment operations quite different from each other. First, he will take daytime ultraviolet photographs of the invisible gaseous layer of ozone that covers the Earth at altitudes ranging from 9 to 31 miles. Invisible ozone is produced by the reaction of solar ultraviolet radiation with oxygen in the atmosphere. Ozone is significant because of the layer of protection it affords us against harmful ultraviolet radiation, and also because of its possible effect on the weather. The second part of this experiment involves both visual and ultraviolet photography of the twilight airglow layers, which are visible only near sunrise and sunset. This airglow results from charged particles reacting to the atmosphere and emitting a light that appears as a glow on the horizon. This data will provide new understanding of the global behavior of the twilight airglow emissions and their possible effect on communications. In the ozone experiment, two 35mm cameras are synchronized so that one camera is taking an ultraviolet picture of the ozone layer, while another camera is taking a visual picture of the terrain feature directly beneath the ozone layer. Later, scientists will be able to determine the actual effect of terrain on the ozone layer above it. Ozone concentration varies with the season and the time of day, indicating a possible movement of ozone through the atmosphere. This cable will synchronize the ultraviolet photography with the terrain pictures. He removes the protective cover from the wardroom window to which the camera will be attached. Next, the crewman installs the camera assembly and connects the synchronization cable. The second 35mm camera, which is used to take the ultraviolet photographs, is located in another part of the orbiting workshop on its own mount, secured to the scientific airlock window away from the sun. The crewman installs the ultraviolet camera assembly and connects the cable that synchronizes the two cameras. He is now ready to begin making exposures of both the ozone and the terrain. He locates special geographic features, such as mountains or a river, tracks the feature by turning the crank, and at the midpoint in his prearranged tracking sequence, the terrain camera will be automatically triggered to capture a companion picture to the ultraviolet shot. The second part of this experiment, the twilight airglow photography, begins as the crewman installs the camera assembly on the solar scientific airlock. The objective is to obtain representative airglow height and intensity data over a variety of latitudes and longitudes. Using his sighting scope, he makes a number of exposures, utilizing different filters. While measurement of the heights of airglow layers have been made from rockets and unmanned satellites, Skylab promises to bring back the most definitive data to date. This experiment will increase our knowledge of two phenomena that may tell us more about our own environment: the ozone and twilight airglow layers around the Earth. In the Earth terrain photography experiment, high-resolution photographs of small areas of the Earth will be made using the Earth terrain camera. The Earth terrain camera and another series of Skylab experiments, Earth resources, view the same portion of the Earth's surface simultaneously. The photographs will be used in conjunction with the Earth resources data to aid in land use planning, in the interpretation of such events as floods and volcanoes, in industrial and urban planning, in the determination of pollution boundaries, crop infestation and damage boundaries, and in the determination of drainage patterns. The Earth terrain camera is a modified version of a lunar topographic camera designed for Apollo missions and may be operated manually for single photographs or automatically for overlapping topographic coverage. Each roll provides for 450 4x5 photographs. Stereoscopic photo coverage of the Earth's terrain is possible by taking overlapping photographs of the same terrain. The stereoscopic results will be of great interest to topographic applications of space photography. He installs the camera window on the airlock and prepares the camera for installation into the window. First, the camera is moved to an upright position. The protective cover is removed and the filter is placed on the lens. Several types of filters are available for use with the different types of film. The crewman begins to install the camera into the airlock. The film is held flat in the weightless environment by means of a vacuum hose. The loaded magazine is placed in the camera. The scientific airlock door is opened. Finally, the crewman sets the controls prior to making the required exposures. This high-resolution Earth photography taken of Earth from a manned spacecraft will provide new knowledge of Earth. The coronagraph contamination measurement experiment attempts to detect and possibly identify the characteristics of small particles in 3 varying space environments: near the Earth, near the Sun, and in the immediate vicinity of the spacecraft itself. Particles near the Earth are important because they play a significant role in our climate and our changing weather. Observations of particles around Skylab will determine the amount of unwanted scattered light which could adversely affect other Skylab measurements. Information about particles near the Sun will help answer questions about the nature and origin of small particles in the solar system. 35mm visual and ultraviolet photographs of particles on the Earth's horizon will be made at sunrise and sunset, while pictures of particles near the Sun will be taken at midday, and the shots of particles outside the spacecraft are taken during other specific daylight periods. The neutral density filter is installed on the camera to allow the crewman to look at the Sun without damaging his eyes. From Earth, it is virtually impossible to make scientific measurements of particles near the Sun because of the brightness of the sky due to particles in the atmosphere. In order to utilize bright sunlight to illuminate the particles without having to look directly into the Sun, a disk will be placed directly in line between the camera and the Sun, thus simulating a solar eclipse. To accomplish this, an extension boom is unstowed and installed on the canister for extending the disk 42 inches beyond the inboard surface. This experiment may prove or disprove the theory that particles near the Sun are caused during times of violent solar activity such as flares. After moving the disk out of the way, the crewman checks alignment and instructs Apollo telescope operator to correct any misalignment by maneuvering the spacecraft. He then removes the neutral density filter and installs a series of filters which he uses to make time exposures. The light, which has been scattered off particles, passes through a quartz window before it reaches the camera lens. This photographic data involving particles in space, particles near the Earth, particles around the Sun, and particles immediately near the spacecraft may help us deal with a growing number of particles within the Earth's atmosphere. These 6 Skylab experiments will have provided us new information about young stars, the Sun, ozone layers, twilight air glow, space particles, micrometeorites, and the Earth itself. The beneficial results of our nation's first orbiting research laboratory, Skylab, will extend far into the future, contributing to the solution of many of the Earth's current environmental problems.